James Webb keeps finding galaxies that shouldn't exist yet, fully formed, chemically evolved, far too structured for the amount of time our models say they've had. Every proposed fix assumes one thing nobody questions, that the time light spent traveling to us equals the actual age of what it shows us. But light, according to special relativity, experiences exactly zero time on any journey, ever, without exception. So what if the assumption itself, not dark matter, not inflation, is where the real problem is hiding? Before I walk you through it, hit subscribe now, because this channel goes deep into exactly this kind of physics, and I don't want you to miss where it leads. Drop your location in the comments, I read every single one. And if this shifts something you assumed was fixed, a like and a share help this reach someone else who'd get pulled in by it too. Before we go any further, I want to be transparent about how this channel works. I'm not going to quote a famous physicist and ask you to take their word for it. I'm not going to tell you what the correct interpretation is. What I'm going to do is walk you through the actual experimental results, the mathematical frameworks, and the verified physical consequences, and then hand the conclusions back to you because that is what intellectually honest science looks like. Not authority, methodology. And if at any point you feel frustrated, hold on to that. Frustration is what happens when your mental model meets something real that it cannot contain. That feeling is not confusion. It's your brain detecting a contradiction that your education never gave you the tools to resolve. Most people run from that feeling. You clicked on this video, so let's go deeper. There are 4 things you need to understand before the central argument of this video lands with the force it deserves. And I'm going to be honest with you, I'm making this deliberately rigorous, not to show off, not to pad the runtime, because if you don't have these 4 foundations locked in, what comes later will feel like philosophy, and it isn't. It's physics, so stay with me. The first thing you need to understand is what a reference frame actually means, not the pop science version, the real one. A reference frame is a coordinate system from which measurements are made. When you're sitting still and you watch a car drive past you at 60 miles per hour, that's the car's velocity in your reference frame. But from the driver's frame, you are the one moving at 60 miles per hour. Both measurements are equally valid. Neither is more true than the other. This isn't philosophical relativism. It's a physical fact with testable consequences. Now here's where it gets serious. Einstein showed us in 1905 that the laws of physics, including the speed of light, are identical in every inertial reference frame. That sounds reasonable until you follow it to its logical conclusion. If light always travels at the same speed regardless of the frame measuring it, then time itself must be what changes between frames, not light's speed, time. The universe adjusts time to protect the speed of light, and that adjustment, as velocity approaches the speed of light, becomes extreme. The universe doesn't protect your experience of time, it protects the speed of light. You're the variable, light is the constant. And once you genuinely internalize that, physics stops being a collection of facts and starts being a single, coherent, deeply unsettling argument. The second foundation is time dilation. And I need you to set aside every analogy you've ever been given, because most of them are wrong in exactly the ways that matter here. Time dilation is not an illusion. It is not a perception trick. It is physically real. We know this because we've measured it. Atomic clocks placed on aircraft flying at ordinary commercial speeds return to the ground measurably out of sync with identical clocks left on the surface. The difference is tiny at those speeds, but it is real, and it matches the equations of special relativity to extraordinary precision. GPS satellites experience time dilation so significant that if engineers didn't account for it, your phone's navigation would accumulate errors of several kilometers per day. This is not a theoretical concern. It is an engineering requirement. Time dilation is as real as gravity. Now here is what the equation tells us when you push velocity toward the speed of light. The time experienced by a moving object, what physicists call proper time, gets smaller and smaller. As velocity approaches c, the speed of light, proper time, approaches 0. At exactly c, proper time equals 0. For a massless particle like a photon, which must travel at exactly c, no proper time elapses, ever, between any 2 events in its journey. The photon that left a star 10 billion light-years away and just hit your telescope did not experience a 10 billion year journey. It experienced no journey at all. In its frame, emission and detection were simultaneous. The journey you measured took 10 billion years. The photon measured nothing. Same event, same photon, 2 completely irreconcilable durations, and both are physically correct. The third foundation is the space-time interval. This is the concept that bridges what happened in the last section to what we are building toward. In special relativity, there is a quantity called the space-time interval, sometimes written as ds squared, which combines space and time into a single geometric measurement. For ordinary massive objects moving through space-time, this interval is positive and finite. For light, for photons, the space-time interval is exactly zero. Physicists call this a null geodesic, a path through space-time with zero length. Think about what that means. Between any 2 points on a photon's world line, the space-time distance is zero. The photon's origin and destination, no matter how far apart they appear in our reference frame, are geometrically adjacent in four-dimensional space-time. The photon doesn't travel across the universe. In a very precise geometric sense, it doesn't travel at all. It simply connects 2 points that spacetime considers to be at the same location. And I want you to sit with that for a moment, because this is where most discussions stop. They give you the fact and move on. But the implication of a null geodesic is not just that light has no proper time, it's that light has no spacetime extent whatsoever. It exists in the most literal geometric sense outside of what we call the universe's timeline. The fourth foundation is the cosmological timeline itself. The standard model of cosmology, lambda CDM, describes a universe that began in an extremely hot, dense state roughly 13.8 billion years ago. In the earliest moments, the universe was opaque. Photons were constantly scattering off free electrons and couldn't travel freely. Then, approximately 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. The universe became transparent. Photons were released. That release is what we observe today as the cosmic microwave background, the CMB. These photons have been traveling for approximately 13.4 billion years. We detect them as a faint, nearly uniform glow of microwave radiation coming from every direction in the sky. Now here is where the question at the center of this video becomes unavoidable. We say those CMB photons are 13.4 billion years old, but from the photon's own frame of reference, they are 0 seconds old. They were emitted and detected in the same instant. So when we say the universe is 13.8 billion years old, we are describing a duration that is real and meaningful for every particle with mass, for every clock, for every observer who experiences time. But light, which is the primary way we observe the universe, the medium through which almost all of our cosmological data reaches us, exists outside that description entirely. We are using an ageless messenger to reconstruct the history of a universe defined by age, and nobody in your education stopped to ask whether that creates a fundamental measurement problem. Now I want you to make a prediction. Before I show you where this leads, I want you to commit to something. Based on what you now understand about null geodesics, proper time, and the CMB, I want you to predict, if light genuinely has no temporal extent, no age, no duration of existence, does the phrase, the age of the universe, have a physically rigorous meaning when applied to light itself? Think about it. Don't just react. Actually reason through it. Because most people, when they first encounter this, go in one of two directions, and both directions miss something important. Some people say, yes, of course, age applies to the universe as a whole, not to individual photons, and the CMB photons are 13.4 billion years old in the only frame that matters, ours. Other people say, no, age is a frame-dependent quantity and therefore meaningless when applied to anything traveling at sea. Commit to one of those before we continue, because in a few minutes both of those answers are going to look incomplete in ways that matter enormously for how we understand cosmology. Here is what the data actually says. The WMAP satellite and the Planck satellite gave us the most detailed maps of the cosmic microwave background ever produced. What they found was astonishing in its precision. The CMB is almost perfectly uniform. The temperature variation across the entire sky is less than 1 part in 100,000, and this creates a problem called the horizon problem. The regions of the early universe that emitted the CMB photons we receive from opposite ends of the sky were, at the time of emission, separated by distances so vast that they could never have been in causal contact. There was not enough time, even at the speed of light, for information to travel between them and equalize their temperatures, yet they are the same temperature. The standard response to this is inflation. a proposed period of exponential expansion in the universe's first fraction of a second that would have stretched a causally connected region to the size of the observable universe. Inflation is compelling. It explains the CMB uniformity. It explains the flatness of the universe. It makes predictions that subsequent observations have confirmed. But here is what rarely gets said in the same breath. Inflation is still a hypothesis, a well-supported hypothesis, but not confirmed. And here is what's directly relevant to our argument. The horizon problem only exists because we're assuming that causal connection requires time. We're assuming that signals need duration to travel. We're assuming the universe's history is a temporal sequence. All of those assumptions work perfectly for massive particles, but photons aren't massive particles, and the horizon problem looks very different if you take seriously the fact that from a photon's null geodesic, the entire observable universe is geometrically connected. I'm not saying this resolves the horizon problem. I'm saying nobody is asking this question loudly enough. Now let's talk about what happened in 2022 and 2023, because the James Webb Space Telescope changed the conversation in ways that are still rippling through the physics community. Webb was designed to see further back in time than any previous telescope. Its first deep field images were breathtaking, but what they revealed was also scientifically uncomfortable. Webb found fully formed massive galaxies at redshifts corresponding to less than 700 million years after the Big Bang. Galaxies that, according to our models of structure formation, should not have had enough time to assemble. The standard model of cosmology says that after the CMB was released, matter needed hundreds of millions of years to slowly clump together under gravity, small structures first, then larger ones, a process called hierarchical structure formation. Webb's early galaxies don't fit that timeline. They are too big, too structured, too chemically evolved to have formed in the time the model allocates. And the physics community's response has been exactly what honest science looks like. Not denial, not silence, but genuine uncertainty. New models are being proposed, modifications to dark matter behavior, alternative inflation scenarios, early dark energy. None of them have definitively resolved the tension. And sitting underneath all of those proposed solutions is the same foundational assumption that we can use light to measure time, and that the time light has been traveling is a straightforward proxy for the age of the structures it reveals. Webb found galaxies that shouldn't exist yet, and every proposed solution assumes light's travel time equals the universe's developmental time. But what if that assumption is where the problem lives? Here's where I'm going to ask you to do something genuinely difficult. I want you to hold three competing interpretations of what we've established simultaneously, without collapsing them into a single answer, because this is where most science communication fails you. It picks the tidiest interpretation, presents it as consensus, and moves on. This channel doesn't do that. So here are the three frameworks physicists and philosophers of physics actually debate when they work through the implications of null geodesics and cosmic time. The first interpretation is the relational time view. This position holds that time is not a background feature of the universe. It's a relationship between physical systems. Specifically, time is what clocks measure, and a clock is any physical system that changes state. Light doesn't change state internally as it propagates. It has no internal clock. Therefore, asking about light's experience of time is not a deep question about the nature of reality. It's a category error. The question, how old is light, is like asking, what is north of the North Pole? The framework that generates the question simply doesn't apply to the subject. Proponents of this view, drawing on the work of physicist Julian Barbour and his investigations into timeless physics, would say the universe's age is defined by the progression of massive clocks, and light simply isn't one of them. The problem with this interpretation, it doesn't explain why light's null geodesic has real geometric consequences for how we measure space-time structure. It answers the temporal question, but sidesteps the geometric one, and that sidestep is not a minor omission. It's where the real tension lives. The second interpretation is the structural realism view. This position holds that what's real are not the objects of physics, but the relationships and structures that the mathematics describes. Light's null geodesic isn't a limitation or an anomaly. It's telling us something true about the structure of space-time itself. Specifically, it's telling us that the universe doesn't have a single temporal structure that all physical entities participate in equally. Massless fields occupy a fundamentally different geometric role than massive particles. They don't evolve through time. They connect points across space-time. And the universe's history, as we reconstruct it from light, is therefore not a direct readout of what happened, it's a projection of geometric structure onto a temporal framework that only applies to part of what exists. The implication of this view is significant. Our cosmological timeline is real and meaningful for the matter content of the universe, but it may systematically misrepresent the behavior of the fields, particularly electromagnetic fields, that we use to observe that matter. Our cosmological timeline is real for matter, but we read it using light, which doesn't experience time. We are reconstructing history with a messenger that has no memory of the journey, and this could explain, at least partially, why Webb's observations keep surprising us. We're reading a temporal map drawn by something that has never lived inside time. The third interpretation is the modified cosmology view, and this is where things get most technically contested, but also most consequential. A growing number of physicists, including work published in peer-reviewed journals as recently as 2024, have begun exploring whether the concept of a universal age is operationally well-defined at all. Not philosophically, operationally. Meaning, is there a physical procedure you could carry out that would give you an unambiguous answer for the age of the universe that doesn't depend on which type of physical system you're using as your clock? For massive particles and atomic clocks, yes. For photons, demonstrably no. Some researchers in this space, including those working on quantum gravity approaches like loop quantum gravity and causal set theory, suggest that time itself is an emergent property, not a fundamental one. That at the deepest level of physical description, there is no time. What we call time is what happens when quantum gravitational degrees of freedom coarse-grain into the smooth space-time we experience. And if time is emergent, then the question of what light experiences isn't a question about a special case, it's a window into the pre-emergent structure of reality itself. This interpretation is the least settled, but it's also the one most consistent with the frontier of theoretical physics in 2024 and 2025. Its strength, it naturally accommodates both the null geodesic result and the anomalies in large-scale structure formation that Webb has revealed. Its weakness, it's radically incomplete. We don't have a working theory of quantum gravity, we have approaches, frameworks, candidates, and none of them are confirmed. So this interpretation is honest about what we don't know in ways the other two aren't, but it also offers the least traction for making specific testable predictions right now. You probably disagree with at least one of those three frameworks. Good, I want you to. Not because disagreement is the goal, but because the moment you feel resistance to one of them, you're doing physics. You're asking, what would have to be true for this to be correct? And is that something I'm willing to accept based on the evidence? That's not a rhetorical question. That's the actual work. Three frameworks, three completely different answers to what light's timelessness means for cosmology. All three are supported by legitimate physics. None is definitively proven. That's not a failure of science. That's what the frontier actually looks like, and most channels won't show you that. Now I want to share where I land on this, and I want to be precise about what I'm doing when I say that. This is not a conclusion. It is not what the science says. It is one interpretation of what the science makes available, and I'm telling you my read of it so that you can push back on it, improve it, or reject it entirely. That's the only honest way to do this. The null geodesic result doesn't feel to me like a category error. It feels like a signal. When a physical framework returns 0 for a measurement, that's usually not a sign that the question is malformed. It's usually a sign that 0 is the answer, and that the answer has implications we haven't fully followed. What I think the null geodesic is telling us is that the universe contains two genuinely different kinds of physical existence. One that participates in time, the matter sector, massive particles, atoms, galaxies, you, me, and one that connects points in time without residing in it, the radiation sector, photons, the electromagnetic field. And the fact that we built our entire cosmological picture, our timeline, our distance measurements, our age estimates, our structure formation models, almost entirely from the second category, while assuming it behaves like the first, strikes me as a foundational assumption that deserves far more scrutiny than it currently receives. Research from groups working on causal set theory, particularly work published in Physical Review Letters in 2024, examining discrete space-time structure and photon propagation, has begun probing exactly this boundary. It isn't mainstream yet, but the questions are being asked, and I think within the next decade, the answer to where light sits relative to time is going to force a genuine revision of how we talk about cosmological age. Not a revolution, a refinement, but a necessary one. I think we've been building our cosmological timeline almost entirely from the testimony of something that doesn't live in time, and I think that's going to matter more than we currently admit. What's your interpretation? I mean that genuinely, not as a comment bait formula, because the three frameworks I gave you don't exhaust the space of possibilities. If you think there's a fourth reading of the null geodesic result that resolves the tension more cleanly, I want to see it in the comments. If you think I've made a philosophical leap that isn't justified by the physics, make the case. This channel exists in the space where the data ends and the interpretation begins, and that space belongs to everyone who's willing to do the intellectual work. Now here's what this episode actually set up, because we've been building towards something, and if you felt it, you're right. The question we spent this video with, whether light has a beginning, whether it participates in time, whether our cosmological age measurements are frame-dependent in ways we haven't accounted for, that question has a direct descendant, and it's this. If time is the thing that light doesn't experience, and quantum mechanics tells us that observation collapses probability into reality, then what does it mean for a photon, an entity outside of time, to be observed? What does measurement do to something that has no temporal position? The measurement problem in quantum mechanics is usually taught as a puzzle about the very small, about electrons and slits. But when you combine it with what we've established here, it becomes something much larger. Tell me what you think in the comments. I read everyone. And before you go, subscribe if this is the kind of physics you want more of. Like the video if it shifted how you think about something you assumed was settled. Share it with someone who needs their assumptions bent a little too. And let me know your location. I want to know exactly who's watching this from where. Do not stop. The next video is already up. The observer has no location. What quantum measurement does to timeless particles? Don't think about it. Don't open another tab. Hit play. Because the thing we established today, that light exists outside of time, becomes the exact foundation that video begins with. And if you stop now, you're going to lose the momentum that makes the next argument land the way it's supposed to. Everything we did today was set up. The next video is where it detonates.